Hello, everybody. This is Brian. I am going to do a review session for two-way ANOVA. I'm pretty new at this Zoom recording thing, so bear with me. It might not be as flawless and seamless as I would like to, but we're just going to go ahead and do it. So we're going to talk about one of my favorite topics for the whole semester, the two-way ANOVA. This is a very powerful stats analysis. The one-way ANOVA, which we talked about last week, we had one independent variable and one dependent variable. And the key was that the independent variable had to have three or more levels, three or more groups that we were comparing the means of. So what we're doing with a two-way ANOVA, the reason it says two here, is because now we're adding a second independent variable. And we're basically doing what we learn, we're getting out of the two-way ANOVA what we would learn by doing two one-way ANOVAs, but we're getting an additional analysis out of it as well, which is called the interaction. So every time you do a two-way ANOVA, you get three primary effects. You get the main effect of each of your two independent variables, as well as the interaction of those two variables on your dependent variable. So under what circumstances can you run a two-way ANOVA? Well, you need to have two independent variables and one dependent variable, and each of your independent variables needs to have two or more levels. And so this is where the vocabulary, again, is very important, just to keep your thinking straight. Like, let's say, for example, we're talking about class year as an independent variable. So if we have our first years, sophomores, juniors, and seniors, it's very important to think of these, this is one variable with four levels, not four variables. And so this could be one of our independent variables, and then we could have, which would be class year. And then maybe we could have another independent variable, like we could have different colleges. I'm gonna write like a 4-year-old here. So we would have maybe Bates, Bowdoin, and Colby as our colleges. And so this would be another independent variable. This one has three levels. And so here would be a good setup for a two-way ANOVA. We have class year as one variable, college as the other independent variable, and then our DV would be whatever we're measuring from those groups. Perhaps, since I'm obsessed with food analogies, perhaps we could do like their satisfaction with their college dining experience or something like that. And so again, we would find three primary effects from this analysis. We would be able to figure out, does class year affect people's satisfaction regardless of what college they go to? So that would be the main effect of class year. And then we would analyze the other variable. We would say college is there a main effect of college, which is to say, regardless of what year you are, does what college you attend affect your satisfaction with the food offerings? And then finally, the new thing that we can get only from doing a two-way ANOVA is the interaction of year and college on the DV. So we would be asking the question, does the change, let's see, how do we say this? Does the difference between colleges change as you change class year? So in other words, maybe at Bates, first years love the food more than the other three, and at Bowdoin, the seniors love the food more than the other three. And so the fact that there's not just differences among the class years, but those differences are different between the different colleges, that would represent an interaction. Confused yet? Yeah, it's kind of, it's a little bit hard to wrangle with at first, but it's a whole lot of fun once you get the hang of it. Let's start in with a different example and figure out how to already solve this. That'll do the trick. All right, so let's start in with a different example. I'm gonna draw some new information up here. So I'm gonna draw what we call a means matrix. And a means matrix is a way to represent, pretend that these are equally sized boxes. A means matrix is a way to represent the different groups that you're comparing in your two-way ANOVA. So I'm interested in movie enjoyment. And so I wonder if movie enjoyment changes as a function of age. So I'm gonna have age being one of my variables, have kids and grown-ups watch some movies. And then I'm gonna choose different movies that have different amounts of violence in them. I'm curious if, so my dependent variable here is going to be movie enjoyment. So I'm already asking the question with my age variable, do grown-ups and kids have a different enjoyment of the movie I'm going to show them? And then I'm also going to show them different types of movies which are rated based on the content, the violent content in them. So for example, we would take a no violent movie, something like Dora the Explorer's Pirate Adventure, which despite the pirate theme, has absolutely no acts of violence in it at all. It turns out the pirate piggies are all nice and non-violent. So there's our no violent movie. We could have the some violent condition, maybe a movie like Forrest Gump, where despite, you know, he goes to Vietnam and has those sorts of violent episodes in his life, he also plays a lot of ping pong and does some running across the desert, that sort of thing. And then we're going to have a third category, a third level of this violence variable, the lots of violent condition. This is your, you know, Saw 4 or one of those horrible slasher movies. So here's our matrix, our means matrix for this two-way ANOVA. We're going to see if there are, as a main effect of age, whether kids and grown-ups have a different enjoyment of the movies. We're going to see if there's a main effect of violence, whether regardless of your age, whether the amount of violence in the movie affects people's enjoyment. And we're also going to see whether there's an interaction. So on my rating of movie enjoyability, we'll say it's a scale of 1 to 10. Let's say the grown-ups who watched Dora gave it a 2. And the kids who watched Dora gave it an 8. The grown-ups who watched Forrest Gump gave it a 4. The grown-ups, or the kids who watched Forrest Gump gave it an 8, because kids just love that stuff. And then finally, the Saw movies, the grown-ups gave it a 6. And the kids did not like this, dropped down to a 2. So this again is called a means matrix, and this is showing the average rating of each of the these 6 different groups in our ANOVA. And since this has 2 variables, the violence variable has 3 levels and the age variable has 2, we can call this a 2 by 3 ANOVA. Okay, so one thing that we're comparing when we're getting these 3 primary effects is the different means that we're interested in here. So for example, if we're looking at the main effect of age, we're comparing the mean of the grown-ups and the mean of the kids, regardless of what movie they saw. So basically, when we want to come up with this rating, we'll call this the A variable. So we'll say A1 is the average of these 3 scores, the 2, the 4, and the 6. So the average is a 4. For the kids, they're the A variable level 2. So the average of the 8 and the 8 and the 2 gives us an average of 6. So when we say, is there a main effect of variable A? Is there a main effect of this age variable? Then really what our analysis is going to do is it's going to compare this 6 and this 4. In the real world, we would need to have like an F statistic and p-value and all these things in order to determine significance. For the purposes of this conceptual discussion, we'll say that any visible difference is a significant difference. So in this case, we would say, yes, there is a significant difference. The kids are giving movies in general a higher rating than the grown-ups. And so that would be a significant main effect of variable A, and where variable A is the age. So now we can turn to the second primary effect from our two-way ANOVA, which is the violence level. This one has 3 levels. So we'll call this variable B. They like to name these variables after famous letters and numbers. They always use A and B. It's completely arbitrary which variable you designate as A or B. I agree that's a bit confusing though. So now we're going to just look at the main effective variable B, the violence condition. So we want to calculate the mean for our Dora movie, no violence, which is a 5, the mean of this 2 and this 8. And then we're going to have B2 here is the mean of the 4 and the 8, everybody who watched Forrest Gump, regardless of their age. And then finally, the mean of the Saw movies, which is the average of the 6 and the 2. And so we're going to have a 4 is the average of those. So when we are calculating, again, we do an F statistic, we get a p-value. And what that main effective variable B would be comparing is these three means, the 5, the 6, and the 4. And this is just like a one-way ANOVA where we're comparing these three means to each other. And it's sort of basically finding out if there's among these three means, if there are any differences. And just like a one-way ANOVA, it could be that all three are different. It could be that one is different from the other two. And so all of your analysis tricks that you learned with a one-way ANOVA would apply to this main effect, since we're looking at three groups. And then finally, we would want to do the interaction. And this is where we find the real exciting part from a two-way ANOVA. Because this is, we only see the interaction when we look at both independent variables simultaneously. And as Professor Douglas said in her video, the interaction is looking at the difference of differences. And so this is the first time we're going to be looking at these cell means, the means in these cells. And we're going to see if these differences are changing. And so, for example, we're going to see, okay, in the no violent condition, the difference between grown-ups and kids was a 6. And in the some violent, the difference was smaller. The difference here is only a 4. And now in the lots of violence, again, the difference is only a 4, but it's in the other direction. So this is an even larger difference because the direction has shifted. And so the interaction is asking the question, are these differences between kids and grown-ups changing as we change the levels of our other variable? And so clearly in this case, it's changing quite a lot. And so we would go ahead and say that this looks like a significant interaction. So this is, again, this is sort of a conceptual approach. Again, we would want an F statistic, a p-value, and all that in order to say it's truly significant. But that's conceptually what we would be learning with our significant interaction. So let's also talk about what follow-up tests would be necessary, because it's a little bit different than you might expect. So for each of these significant results, each of these main effective A, main effective B, and the interaction of A and B, there's a possibility of needing to do post hoc tests or follow-up tests when you find a significant result. So let's go through one by one. So if we find a significant result for variable A, what post hoc tests are necessary? Well, in this case, we only have one set of values that we're comparing. We're just comparing the 4 to the 6. So we find a significant result. There's no follow-up test needed because we know that the 6 is significantly higher than the 4, and there's no ambiguity about where that significant result is coming from. So that would be the end of any analysis if we find a significant main effect of A. However, with a significant main effect of B, we would need to do post hoc tests, and this would take the form of like Tukey's test or one of those that we did for the one-way ANOVA, because we would want to figure out, okay, is the 5 different from the 6? Is the 5 different from the 4? Is the 6 different from the 4? So basically, which pairs are different among all three of these means? What is the pattern of the significance? Just like we would if we were conducting that one-way ANOVA. And then lastly, for our significant interaction, we would want to do, whenever you find a significant interaction, you always do a follow-up test, even in the simplest type of two-way ANOVA. If you just had a 2x2 ANOVA, if you find a significant interaction, you would still do the follow-up tests. And the follow-up tests are called simple effects tests. I'll write that out here. Sometimes they are called, just to be really confusing, simple main effects tests. Not to be confused with the regular main effects, but the simple main effects or the simple effects tests are basically chasing out all of these pairwise differences or intercell differences that we're talking about in order to describe the pattern of the interaction that we found that was significant. So another way to look at these is with a graph. So I'm going to go ahead and draw a graph here. It's going to be a good one. So whenever we draw graphs in the context of a two-way ANOVA, how do I go? There we go. You're always going to have your axes, and all of the labels that we've had so far, our y-axis, so far in this course, our y-axis has always been frequency. That is changing now. Our y-axis is always going to be our dependent variable, which in this case is enjoyment of the movie. So we'll go ahead and put that in there. And then on our x-axis, this is where we're going to break this down into one of our independent variables. And so we're going to grab, perhaps, I don't think I'm going to be able to grab from there, but we're going to recreate our violence conditions here. So we have none, some, and lots represented as little, we'll do little tick marks here on the line if we can. Doop, doop. Those are perfect. Those look like maybe an 8-year-old drew them, not a 4-year-old, so moving up in the world. And then what we're going to do to represent the height on our y-axis is now we're going to incorporate our other variables. So we can just take this means matrix and turn this into a graph. So I'm going to draw in here my grown-ups line first. So we'll put them at about a 2 and about a 4 and about a 6. And we can connect them with this haphazardly scrawled line. And then we'll put our kids' stuff on here. We'll use a different shaped cursor. And then, oh yeah, pretend all those lines are straight and all those dots are lovely. And we'll go ahead and use a little bit of text here. And so we'll mark this is our ups with the solid line and our kids with the haphazardly scrawled dotted line. And so this is a way that you can see in a different format the results here. And we'll do a lot of work with these types of graphs in just a little while. But I wanted to communicate to you that if you have trouble interpreting a means matrix like we have above, sometimes it can be helpful to turn it into a graph, and it might make more sense to you as a graph. And conversely, if you have a graph and you're having trouble with things in graph format, maybe you could turn it back into a means matrix and calculate some of these marginal means, the means out to the side of the graph of the chart, and it might make more sense to you in that format. So, but I basically just converted this means matrix into this graph. And the real key with an interaction, I find the interactions are the things that are easiest to see when you're looking at a graph, which is that if the lines aren't moving together, then that suggests that you do have some sort of interaction going on, because that's getting at this idea of the difference between the kids and the grown-ups here, and the no violence condition, for example, is changing as we change the levels of violence. The relationship between kids and grown-up score is changing as we change the amount of violence in the movie. And so that's what conceptually this interaction is telling us. All right, before we move into other graphs, I did want to talk a little bit about the ANOVA table. This ANOVA table, I'm going to clear all this. Whoa, there it goes. All right, this ANOVA table, I'm not going to do a full out ANOVA table because it follows the same principle as the other ANOVA tables that we've worked with, in the sense that we have these column headers representing the sum of squares, the degrees of freedom, the mean square. We're going to turn those into an F statistic. I'm going to turn that into a p-value. Come on, work with me here. There it is. And then we would finally have, I don't know how to do eta squared in my computer, but we'd finally have an eta squared, just like we did with the one-way ANOVA tables that we were working with. But of course, we have more going on. Since we have 3 primary effects, we're going to have an A, a B, an AB. We have our error term, which is called the within cell. Non-traditional double equal spelling. And then finally, we would have a total. So go ahead and put some haphazardly drawn rows in here. So this looks like it's not drawn by chimps. All right. I'm not going to do my other column. So basically, the relationships are all the same here as we're used to from the one-way ANOVA. The ratio of the sum of squares of the degrees of freedom is the mean square, and so on like that. So the big thing that we need to learn here is we have new degrees of freedom formulas. So the degrees of freedom for our A variable is P minus 1, where P is the number of levels of our A variable. So we called our A variable in our example was age. So in that case, it's just going to be 1 because we had grown-ups and kids. We had 2 levels, so 2 minus 1 is 1. For our other variable, our violence, we had the degrees of freedom formula for that is Q minus 1. In this case, we had 2 degrees of freedom because we had 3 levels. And then the interaction is the product of those 2 degrees of freedom. So we can write it out as P minus 1 times Q minus 1. And so in this case, it'll be the product of the other 2 previous degrees of freedom. The within cell is also a new one. It's big N minus P times Q. Again, where P and Q are the number of levels of our A and our B variable. I never said this when we were doing our example, but let's assume that we had 6 people in each cell. So we have 36 total individuals split into 6 cells. And so then we're going to have 36 minus 6 is the calculation here. I'll write this out more explicitly. So we have 2 levels of one, 3 levels of our other. And so that means that our degrees of freedom within cell is going to be 30. And then our last degree of freedom is familiar to us, big N minus 1. Big N is the total number of participants across all of our conditions. And so that's going to be 35 in this example. So again, this isn't new conceptually. We have some extra rows since we're doing the 2-way ANOVA. We're going to have 3 F statistics because we're going to, and 3 P values. We're going to have an F and a P for our main effective A, an F and a P for our main effective B, and an F and a P of our interaction. But the same is still true for all of our sums of squares here are going to add up to our sum of squares total. It's also true that all of our degrees of freedom are going to add up to our degrees of freedom total, in addition to having this formula. With the mean squares, we're going to have this mean square within cell, the ratio of the sum of squares. So the mean square within is going to be the ratio of the sum of squares over the degrees of freedom. And this is going to be our error term for all of our F statistics. So basically, we're going to take the mean square of whatever row we're on. In order to calculate this F statistic, we'll divide it by the mean square within cell. So all of our 3 F statistics have the same denominator, which is the mean square within cell. However, they might have different p-value, or I'm sorry, they might have different critical values, because notice that the critical value we're going to be comparing this F obtained to is going to be 1, 30 for my my F of A, whereas my F of B and my interaction, I'm going to have 2, 30. So I'm going to be looking at a different spot on my critical value chart for my F table, just because the degrees of freedom are changing. And depending on exactly how many levels I have, it could be that all 3 of these have different degrees of freedom. In our case, the A is different, and then B and AB are both the same. But be cautious about that your degrees of freedom are very likely going to be different, and therefore your critical values are going to be different for each of your 3 different F results. So I won't do a full-out example of the ANOVA table in this. I put out a problem set on Lyceum, and there's some examples for you to fill in there. One warning I will give you is when you're dealing with SPSS, SPSS likes to, it has all this stuff, but it has some other things in here as well. So one thing that SPSS does is it starts off with 2 columns or 2 rows that you should totally ignore. It's called corrected model. You don't want that. That's going to come before the A. And then right after corrected model, it says intercept. You want to ignore both of those. And then down here, before it gets to the total, what it has is, it has, in SPSS, there's 2 total rows. First, it lists the total, and then below that, it lists the corrected total. And in SPSS, we want to, this is the one, we want the corrected total, and we want to totally ignore the SPSS total because it's bogus. We also want to ignore these two. And so basically, SPSS is going to give us 1, 2, 3, 4, 5, 6, 7, 8 rows, and we want to focus in on the correct ones. So when you're looking at SPSS, the thing we're thinking of as total is labeled corrected total. You want to ignore this corrected model and intercept rows in any SPSS output. Otherwise, it's going to be laid out exactly the same way as we're looking at here. Okay, moving on, I want to clear all this again. And I want to talk a little bit more about graphing. So the exercises that she had in class can be a little bit tricky. So I wanted to do some examples here. We're going to create a big set of axes here. And again, we're always going to have our DV as our y-axis label. And one of our variables along the x-axis, and then the other one represented as different lines on our chart here. In her video, she suggested coming up with concrete variables. You know, the exercises she gave didn't have variables. It was just like, is there a main effective A? Is there a main effective B? If she does that on a quiz, then you should try and come up with some concrete labels just to think about it in a way that makes a little bit more sense. So let's go ahead and put some text in here. Simple with just 2 levels of B. And again, the B and A are arbitrary. So you could have the A's on the graph on the x-axis label, or you could have the B's down there. It doesn't really matter which is which. So let's start off with a simple example. So there's one line, there's another. We'll go ahead and label this. This will be A1, and this will be A2. So we could ask the question, is there a main effective variable A? Is there a main effective variable B? Is there an interaction of AB? And we can also talk about some simple effects. So in this case, first of all, let's start with the main effective A. So basically what we're saying is, okay, let's go back to our idea of grown-ups and kids. So, we want to, in order to evaluate the main effective A, we want to say, all of the grown-up scores, do they average out to be different than the average of all the kids' scores? And so in this case, grown-ups for both of our B levels are scoring higher than the kids. And so I would say that the average of all the A1's points are going to be higher than the average of all the A2 points. And so I would say yes, in this case, there is a main effect of variable A, a significant main effect of variable A. And then for B, we're going to sort of slice it the other way. Now I want to look, you can imagine that there's little nodes here on these lines. Pretend that these stop at the right point. And so for the main effective variable B, I want to calculate an average of B1 and compare it to the average of B2. So again, now I don't care about the different ages. So I want to say, okay, everybody who has a score at B1, what's the average of all those? And I would say it's about there, right between those 2 dots. And I want to compare that to the average of B2. So again, for B2, I'm going to average between those 2 dots. And the thing I'm really interested in comparing is the height on the y-axis. So do these guys have about the same height on the y-axis, the B1 average and the B2 average? And it looks to me like they do. And so in this case, we would say, no, there's no significant main effect of variable B because this movie violence, let's say, is not changing as I go from level B1 to level B2. And then for the next one, the interaction. This one I think is pretty easy to see in a graph. We want to see, are these lines moving together or are they staying, or are they moving in different ways? I'll just erase most of my graph there. Interesting. Let's put this back in. La, la. And so these lines are moving together. The difference in my grown-ups and kids in the B1 condition is not different than the difference between the grown-ups and kids in the B2 condition. So I would say that no, there is no significant interaction here. In her exercises, she had additional drill downs where you could talk about simple effects, where you are, in simple effects, what you're doing is you're isolating one level of your variable and looking for differences in the other level of the variable. And so in this case, I want to just say, okay, let's ignore the fact that I showed anybody any movie besides Dora, Dora the Explorer. So did grown-ups and kids have a different enjoyment of the movie when I just showed them this? And that's basically saying, are these two dots different on my y-axis? So yes, they are. We would say that that is the difference of f of a at b1. I'm isolating the b1 variable, or the b1 level, and I'm looking for a difference in my a variable. And so in this case, I would say, yes, there's a significant difference. And I could do the same. I would say f of a at b2 has the same difference. So let's slice it the other way. I can look for f of b at a1. Now in this case, I'm trying to see if movie violence, my b variable, had a difference just for my grown-ups. I'm isolating the A1 level of my age variable, and I'm saying, just for grown-ups, did the amount of movie violence affect people's enjoyment? In this case, they didn't, because the grown-ups, again, this is the height on the y-axis, gave it about the same rating in the B1 condition as in the B2 condition, and so I would say, no, this is not a significant main effect, or simple main effect of f of b at a1. So this is sort of the role of the simple main effects, is to sort of slice these guys in different ways and see where you have significant differences and to describe that pattern of the interaction. So we can do this with other examples. So let's draw a different pattern on here and see if I can do something without erasing everything. Oh, that's a better start. Can I erase? Yeah, all right. Well, okay, so new example. Get some lines going on here. So what if we had something that looked like this? Get those about the same spot. So we'll call this A1. This, wow, I'm always one letter off. And again, our y-axis is our dv. So what about this new pattern? So let's start with main effective A. Is there a significant main effective A? Just by, again, in the real world, we would want to use an F statistic, get a p-value, and all that sort of stuff. But for our purposes here, we're going to say any visible difference is a significant difference. So is there a main effective A here? Well, yeah, I think so, because again, like the previous example, the average of the A1 points, I'll draw some points in here, average of the A1 points are uniformly higher than the A2 points. So the average of this guy and this guy is going to be somewhere, here. And then the average here of the A2 points is going to be there. And so the difference here is going to be that significant difference of my main effective A. So now let's look at B. So again, B, we want to isolate just the B1 points and figure out what the average of those would be. It'd be right there. And then isolate the average of the B2 points, which would put it right there. And so this is the height on the y-axis here is substantially different from the height on the y-axis for that guy. So in this example, I would say, yes, there's a significant main effect of B as well, because clearly both groups have a low enjoyment rating in the no violence condition, and then in the some violence condition, yeah, it's gone up quite a bit on average, if not for both groups. So yeah, that's a significant main effect of variable B, our violence condition. And then lastly, the interaction. We would say in this case, there's no interaction because the difference between kids and grown-ups is remaining the same as I change the amount of violence. They're both increasing, but they're both increasing by about the same amount. So that increase is reflected in the main effects, but is not reflected in a change in the difference between them. So I would say that there's no significant interaction in this example. And again, we could break this down into those simple main effects, f of a at b1, saying, yes, it looks like that kids and grown-ups have a different enjoyment in the no violence condition. Or for example, the main effect of B at A1, where we just isolate the grown-ups and we say, okay, do grown-ups movie enjoyment change as we change the movie violence? And in this case, I would say, yes, we do that as well. Okay, so those are some fairly simple examples. Let's do something a little bit more complicated. I don't want to nuke everything here, so let's see what we can selectively clean up. Just erase all that, I guess. Okay, what about something that looks like this? Get some text in here. So pretend for our own purposes here that these come down and these meet in pretty much the same spot, whereas these are pretty far apart. So we can ask these same questions. Is there a main effect of A, main effect of B, and an interaction of A and B? So let's start with A. So with A, I would say, yes, there's still a significant main effect here, because even though for the no violence, the rating is the same, that the grown-ups like the more violent movies a whole lot more. And so that's going to bring up the overall average for this some violent movie for the A, for the grown-ups, whereas the kids are still staying the same. So the fact that the grown-ups are going to overall have a higher enjoyment rating is going to give us a significant main effect of the age variable, the variable A. And now we can look for the main effective variable B, and here we're going to see the average. Well, it's pretty much right there for the B1, the rating for the no violence, and then it goes up, but solely as a result of the grown-ups increased ratings. So, but when we just look at the average of all the B2 points, that average is higher than the average of all the B1 points. So I would also say, yes, we have a significant main effective B. And here we do see a significant interaction, because we can see that these lines are not moving together, that only the grown-ups line is increasing as we go into level B2, whereas the kids line is not changing. And so that the fact that the difference between grown-ups and kids is not the same for each of our levels of B is what points to a significant interaction here for this, this analysis. And this is also where it might be interesting, now that we have a significant interaction, we can do these simple main effects, f of A at B1, for example. We're just going to isolate the B1 and say, is there main effect of variable A, the age variable? And I would say that no, there is not. However, f of A at B2, yeah, this is where we're seeing that age is making a big difference when we just look at the some violent movies. And so I'll scroll in here. And so this would be an example of how these simple main effects are showing us, exactly what's going on. Why did we get a significant interaction? And we can describe this by saying, oh, well, the kids and the grown-ups are effectively the same when we show a nonviolent movie, but as soon as we show them a different movie that has some violent content in it, now the grown-ups have a much higher score than the kids. And so that's where, that's why we're getting a significant interaction. And we can see that in these simple effects tests. We could slice it the other way. We could do f of B at A1. We're just going to look at grown-ups and say, does the violence affect grown-ups ratings? And the answer is yes, that as we add violence, we're increasing their enjoyment, crazy grown-ups. Whereas for f of B at A2, now if we just isolate the kids, we see no significant effect in that result, because the kids ratings are not changing regardless of the amount of violence in there. So you don't have to do both of these. You can do whichever one makes more conceptual sense, because they're both different ways of describing the pattern of the interaction, but they're a little bit redundant. So whichever one is easier to interpret or sort of makes more sense to you is the direction you have to go. You don't have to do both pairs of these, but you should do one set of these when you have a significant interaction. I'll do one more. Let me find my magic eraser here. Get things cleaned up. Maybe a little more than I want to, but there we are. Okay, do one more example. Let's put just for complexity's sake, let's put 3-level variable here for B3. Let's go something like this. And then, oh, that's beautiful. I'll go ahead and put in, pretend these guys are right over each other. So I have dots there. And to differentiate these variables, I have X's for one and dots for the other. So these line up in the middle. That's somewhat clear, right? Somewhat. Okay, so let's talk about our analysis here. So this is, we can look for the three primary effects, A, B, and AB. So for the main effect of A, and this is a little swirly, so let's proceed carefully. So let's call that A1 and that A2. And so for the main effect of A, I want to average all the A1 points together. So there's that one, and that one. You can think of like a high, medium, and a low for A1. And that's going to average out to be about the same as the high, medium, and low for A2. They're arranged differently, but sometimes it helps if you have, like in this case, our y-axis doesn't have labels on it, but if I just want to say, well, that looks like about a 10, it's about a 5, that's about a 1, you can create a means matrix like I was suggesting earlier in this presentation. And we would see that the average of the 10, 5, and 1 for A1 is going to come out to be about the same as the average of the 10, 5, and 1 for A2. And so I would say that there is no significant main effect of A, that the changes are sort of canceling each other out. Along the same lines, I would say we have no significant main effect of B either, because if I look at the B1, it's going to average out to be about a 5. And the B2 averages out right there too. And then the B3 is also the average of these 2 points. It's going to be right there on the same place on the y-axis. And so as I change the amount of violence in the movie, I'm not really seeing a change in the average enjoyment scores, even though clearly I have different things going on, but the average for B1 is going to be about the same as the average for B2 and the average for B3. So I would say there's no significant main effect of B. And then for AB, yeah, this is where we have the real magic happening. And so I would say, yes, this is significant interaction. Clearly, the lines are not moving together. The grown-ups, well, let's go in a way that makes sense. So the grown-ups really didn't like the nonviolent movie, but the kids loved it. They were sort of all about the same in the some violent movie. And then we had the exact opposite reaction. The grown-ups love the violent movies, and the kids hated the violent movies. And so that sort of complete switch in their opinions is what's leading to our significant interaction here. And this is a real demonstration of how cool the two-way ANOVA is, because if we just did this as two one-way ANOVAs, first we looked at age, and then we looked at the amount of violence, we wouldn't see anything at all. All those sort of differences would just cancel each other out. But looking at this with a two-way ANOVA, we see in the interaction that there's actually something very cool going on here. And this is called a crossover interaction, because the lines are crossing there, and we're not seeing the significant main effects, but we are seeing some cool stuff going on with our interaction. And so that's sort of my final pitch for why 2A ANOVA is a very cool analysis. I think for your quiz, it's going to be this more high-level conceptual stuff, understanding how to interpret what is a main effect, what is an interaction, what types of follow-up tests you would need to do if you find significant results for any of those tests. You should be prepared to draw graphs, to analyze graphs. You should be prepared to complete an ANOVA table. So that's something to practice with a little bit. Or look at a means matrix and understand what kind of information is in a means matrix. And so those are sort of the high level ideas. Like, you won't be expected, I think, from raw data to go ahead and calculate like the sum of squares. I know she did that in the video. And it's good to have that exposure, but I think that's beyond, this is, a 2A ANOVA is a great argument for doing stats analysis with a computer, because as you can see from her videos, the calculations from raw data do get pretty cumbersome pretty quickly. So there it is. That's the material I prepared for 2A ANOVA. So thank you for your attention. And certainly find me on my office hours, or you can send me an email or set up a Zoom appointment with me, and I'm glad to continue the discussion. And I hope you're all doing well, and I will talk to you soon.